Hi, everyone. Let's get started. My name is Brian O'Connor from the Open Networking Foundation, and I'm going to be co-presenting this talk with Devjit Gopalpur from Google. Still there? So this talk is about escaping vendor lock-in through open switch interfaces and software. So let's start by defining the problem. So single vendor networking makes life easy. The majority of networks deployed today, or at least small-scale networks deployed today, you have a single vendor that provides an aggregation switch, top of rack, spines, an EMS, an NMS. And this all works wonderfully well. It's integrated. Things are great. Until you want to start changing things. And this is where we start to see a classic example of vendor lock-in. Explicitly, it may be difficult or impossible to change or replace the individual blocks with other vendors' components. And implicitly, anything that you start to build on top of this infrastructure, whether it be orchestrators, and other applications, value-added features or services, is going to be implicitly locked into this architecture and this solution, which amplifies the vendor lock-in. It makes it very difficult or expensive to move away from this model. So why don't we just go multi-vendor? This is an approach that a lot of the bigger vendors are starting to take, a lot of the bigger operators, service providers, cloud operators. They need to take for a variety of reasons, including performance, features, cost, optimization, and also just so they aren't dependent on a single vendor for their business. But this creates a lot of questions. And those questions are things like, how do I understand the idiosyncrasies of the protocols that are used in a given box? What are the models that are in use? What's the pipeline for the ASIC that I'm using on this particular box? Typically, these boxes will come with EMSs, which will help to understand some of these idiosyncrasies, but then they're going to export different models and protocols that you need to adapt to at higher levels. One of the first questions you'll get is which NMS, which network management system should I be using in a multi-vendor network? And it's not necessarily clear. Maybe you can use vendor 1 or vendor 2s if they have a relationship. Maybe you have to use both. And now we have an additional higher level orchestrator that's going to create an additional level of complexity. And what it comes down to is either way, whichever way you go, anything that you are going to build, the services and value add that you're going to put as an operator on top of this are going to still be locked in. So we still have a lock-in problem. It's just with 2 vendors rather than 1. So what are some of the solutions that we've seen in the industry over the past couple years? Well, the first approach that's been generally adopted is a least common denominator approach. You could say IP tables are good enough for my use case. I'm just going to use Linux IP tables. Microsoft and several of their partners have been pushing forward a switch abstraction interface called SI, which works for their use case. It's good because you're not necessarily locked into a single vendor anymore, but it's really difficult in general to extend these interfaces without recompiling and rebuilding the whole stack. And the other thing about least common denominator solutions is they work for what you want to build today because you understand your requirements today, but they make it difficult when new hardware becomes available to exploit unique capabilities, like programmability, like new tables, like additional types of peripherals that you'd want to attach, like maybe FPGAs. So what's another approach? Well, another approach is to underspecify your interfaces. This is something we've seen with OpenFlow and ONS flow objectives. What you do is you basically just provide some basic semantics, but don't really fill in all the details. And this is more easily extensible. There may be some vendor-specific nuances, but in general, it's easier with OpenFlow or flow objectives to describe or use different pipelines. But in practice, the upper layers of the stack are going to need to be written to specific targets. And this leads to our third solution, which is the single vendor solution. Use the single vendor's SDKs, APIs, and models. It's really easy to exploit the hardware capabilities, but the problem here is solutions are not typically portable or reusable. And this in practice tends to be the only solution that performs reliably in production and scales up to sort of the limits of a given box. So the solution to multi-vendor SDN is single-vendor networking. And this is sort of a cycle that is created a problem for the networking industry and something that we hope to present a solution for today. So our next section, Devjit's going to walk through.
So thank you, Brian. So that leads us to some of the unique problems that we face in trying to deal with the network at Google. So how do we map this? So we have a centralized control plane, disaggregated in other terms. And we have all of the relevant network applications running on top of a flow programmer, which control the entire universe of switches. Of course, partition into domains for high availability, etc. So think of a domain, and there is a controller with leaf spine fabric. So what are some of the fundamental problems we have? So we've been very successful using OpenFlow for extensibility, as Brian mentioned. But now that also leads to the problem when we need to add new features. We would have to rewrite the switch stack, which means rolling out new software to thousands of switches, and so now your rollout to production is weeks, if not months long affair. So how do we bring in new switches with new interfaces which don't tie into maybe OpenFlow or any of the interfaces that we're familiar with? What we want to do is sort of explore some new interfaces that can tie together the heterogeneous set of devices that are available, and then be able to plug them into this heterogeneous network here. So what are we looking for in order to get to this, to evolve into this new generation of SDN? So we want to be able to write control applications. We want to be able to express a network intent in a vendor-neutral manner. What that means is, we write once, but be able to apply that to multiple devices. So we want a contract that is extensible, but almost in a sense immutable. So so that if you want to deploy some new software, if you don't, you just have to write the extended form of your control plane application, and you don't have to really change anything in the back end to just roll out a new network role or something. We want to be able to support new hardware, the new generation of programmable hardware. So the interface should be extensible again, but support programmability in the back end. So what that means is that this the flexibility that this is providing is that the control plane and the applications are more faithfully reflecting what the backend really is capable of and can provide. So we push, in other words, we push the abstraction up up the stack, up the network stack. Another aspect is management. So we want to be able to express our topology in a uniform model so that we can bring in devices, enable multiple vendors to be able to, or enable devices from multiple vendors to fit into the same topology to coexist with the hardware from other vendors. So we want to be able to develop a vendor agnostic model, and what that means is life becomes easier for the operators who can now sort of use common tools to manage and operate the network. So now this is really important for for innovation at the cadence that we really want. So we want to be able to focus on optimizing our network functions. We don't want to be spending our time figuring out how to extend our APIs and the interfaces to be able to support this. And which eventually will help us migrate all of the services that we run on top of the current devices to newer devices and across multiple vendors. And as I mentioned, have a uniform management tool that talks the same set of interfaces to different devices. So we come up with a control interface that is called P4 runtime, which is essentially an API, a set of APIs which sort of derive from the portable switch architecture model, the reference architecture, but we extend that to also support the traditional fixed pipeline switches. So with the advent of white boxes and with more vendors supporting programmable switches, we want to bring in an interface that is extensible and can support programmability. So this interface is basically a gRPC-based interface which uses P4 for the definition of, so for the control plane definitions, we use a P4 program. We'll see in a minute how we can sort of use that to make this vendor agnostic. And also, an important feature is that this allows for runtime configurability of the data plane. So what the network operator has to do, or a network designer has to do, is just recompile a new P4 program to the same backend and then define new network roles and have that deployed at a much faster pace. So I mentioned P4. So let's just take a moment to see what P4 really, the role of P4 here. So so P4, I guess everybody knows, is it's a formal definition language that can describe the forwarding pipeline. Now, the important thing that we do here is that we use we use the P4 runtime aspect to sort of make this portable to different architectures. So you could have a programmable ASIC, or you might have a fixed pipeline ASIC. What P4 gives you is sort of the logical view of the network intent, and your backend implements based on the switch provider, implements that in the respective hardware pipeline. So the compiler, how do we achieve this? So there is a, so let's say you have your P4 for a specific role. You compile your P4 program with the compiler for that specific target, which produces two different parts of the output, which are a target-specific set of binaries, which we call as the device info, which is used to basically initialize the ASIC. So when you push the forwarding information, the ASIC uses this to sort of initialize its memory to do some memory allocation or to power on the ASIC, etc. So that's what the first part is. The second part is the P4 info, which is basically the core of the program, the P4 program, which describes the relationships between the lookup tables, and the actions and the parameters associated with that. So this is expressed in protobuf format. So it is portable to different types of hardware, whether it's programmable or a fixed pipeline. So how do we put all of these together? So let's say you have a programmable ASIC and you have fixed pipeline ASIC from two different vendors. So we have these. I'll tell you what Stratum agent is in a moment. But the Stratum agent runs this P4 runtime service and talks to a generic controller such as the ONS, which is hosting some of the applications that your network would like to run. And so we compile the role-specific P4 program to push the P4 info to both the control plane and the data plane. And the P4 info is then used by the P4 runtime to program the runtime information such as flows, for example, a lookup into a specific table and which applies a certain action. So the P4 info is giving you the schema to match the table ID, the action ID, etc., into like specific tables and lookup entries in the specific hardware. And this would be different among the different hardware that you see here. So on the management aspect, we talked about trying to have a uniform network model. And so we have a bunch of things that we want to control on the board, such as fans or your power, get status about your power supply, or even programming certain the scheduler or the cause queues, etc., on the NPU. So we use GNMI. And this is used for streaming telemetry and for configuration. GNMI, so the GNMI again, so it's based on the open config model. So you express your the topology that you would like that you would like to. So the topology is expressed in terms of components in OpenConfig, and GNMI is the interface that a management entity would talk to, like a GNMI service in the Stratum agent, and which basically provides streaming telemetry and enables like a vendor neutral view of the network. And similar to a P4, the OpenConfig model also gives you the ability to sort of extend your network model, and all you have to do is basically recompile, and as long as your backend supports a specific entity, you just have to. So GNMI gives you the ability to just regenerate a topology and then push, this specific configuration element to the device, and also be able to subscribe to the notifications for that, the new component that you just added. GNOI is a set of microservices that enables services like operations like rebooting a switch or running some diagnostics and file management, etc. So this can also be based on the model that you generate with OpenConfig. So putting it all together, you have a Switch OS, and this is what the Stratum agent gives you, which is the set of services in GNOI, GNMI, and then the P4 runtime service for the control plane. And this gives you the next-gen SDN picture where you have a set of devices that are all running Stratum, a heterogeneous set of devices talking to a generic SDN controller that is then talking to Stratum using the interfaces that we just talked about. And now Brian is going to talk you through the rest of the talk about implementation and some exciting test framework.
Thanks, Devjit. So open interfaces and models are a great place to get started. They're definitely necessary for enabling a multi-vendor network solution, but they're not sufficient. And they're not sufficient for a couple of reasons. The first is that interfaces are typically written in English, or at least the description of semantics are written in a language that needs to be interpreted by a human and then programmed. And there are mistakes that happens when that occurs. So interfaces are best when they're defined in running code. And so providing an open source implementation will help solidify the interfaces and models. And it's more than just a standard exercise. These interfaces are not done in a room and then thought about. I mean, it's actually an experience that you get by writing code, modifying the interface, and there's a virtuous cycle that happens there. The other thing is that if you just have an open source implementation that is not necessarily production targeted or ready, there's going to be bugs in other people's implementations that are going to need to get fixed. There's going to be deviations in those implementations. So by providing an open source and fully production ready distro, we hope that we can avoid a lot of the bugs that occur in systems due to variations in implementation. This allows you to fix things in one place, reduces R&D cost, and improves time to market. So from a design perspective, when Google started the Stratum project and as a community, some of the principles we've adopted are first and foremost chip, platform, and data plane independence. That was something that Devjit just talked about. The second is we wanted a set of generic and common APIs that enable not only local configuration and control, but also remote control. So we wanted to be able to locate pieces of your control and management plane off the box. What feeds into that is also having a lightweight system, having something on the box that has a minimal set of dependencies, is easy to deploy, a minimal set of system requirements, so you don't have to require a lot of the CPU cycles to get things up and running. And lastly, we wanted Stratum to be reusable and extensible. So not only at the northbound, but also throughout the Stratum codebase, we have a set of interfaces, common interfaces, that can be leveraged and reference implementations of those interfaces. The architecture is flexible enough to accommodate new chips and new platforms and the features or value that they want to add, but not so open that there's going to be wide deviations from platform to platform. And then in general, the Stratum community has adopted an approach where we prefer third-party work when it's applicable or appropriate. For example, for ONL, for the peripherals, we tend to prefer Open Network Linux Peripheral API, or ONLP. From an architecture level, this is the building blocks that we have in place. Stratum, as we mentioned, is something that runs on the box, so there's going to be a Linux kernel with platform drivers and the Switch ASIC drivers. There'll be SDKs and APIs for those that get exposed to user space. Then on the left-hand side of the screen, we have, in the green boxes, a set of abstractions and interfaces for managing the mappings from P4 runtime down to the Switch SDK. And in Stratum today, we have two different implementations. One is the FPM-based implementation for fixed function ASICs, which translates from the high-level P4 runtime messages down to the SDK of a fixed function vendor. And then on the programmable ASIC side, we have a PI implementation. So you're not necessarily going to see L2, L3, and ACL in the PI side because those are just P4 constructs that get passed through the SDK. But nevertheless, it's the same interface that gets exposed up from those two implementations. On the right side, we have a platform manager, and the reference implementation that we have is based on ONLP. So any ONL-based box should be able to conform to this platform manager. And then a chassis manager ties this together. It's what ties the front panel ports to the ASIC ports, what manages the serialization, CERDES, the serialization, deserialization of the transceivers, and then also does things like box and ASIC initialization. Sitting on top of this, we have a broker interface that provides a boundary between the box-specific mappings and common implementations of P4 runtime, GNMI, and GNOI. So every Stratum implementation will share P4 runtime, GNMI, and GNOI, and by sharing the code at that layer, that's how we help provide common semantics across different boxes. If you're interested in some of the nitty-gritty, Stratum is a user space process running in Linux. You can distribute it with ONL or really any other modern Linux distro running a 3 or 4 Linux kernel. We built it using Bazel. We wrote Stratum in C++ using the 11 standard. And then, if it wasn't clear yet, each of these services that we have is a gRPC-based service. And you can run your clients on the box or off the box, depending upon your network architecture. So that's Stratum in a nutshell. And so the question is, OK, we have open interfaces. We have an open implementation. Is that good enough? Is that good enough for multi-vendor networking? And the answer is not quite. The open source implementation provides a good amount of direction for interoperability, but there are still going to be implementation discrepancies that happen down in the mapping layers and down in the platform layers. So what we need to do, and there's going to be other implementations too. It's not just going to be Stratum as the only implementation of these interfaces. And those implementations and those boxes will need to be qualified. So what we need to do is we need to have a vendor-agnostic black box test framework for any target that wants to comply with this new set of next-gen APIs or the Stratum Open APIs, along with a repository of tests for those. So something the Stratum community is beginning to develop is a test framework we call test vectors. And it starts with test cases. So a test case is going to have a set of stimuli. These stimuli are typically going to refer to the open interfaces. I want you to make this P4 runtime call or this GNMI call with this model. And then there's going to be a set of expectations that are the output of those series of stimuli. So these test cases, then if you have one or more test cases in a given area, they can be bundled on a per module or per target basis and stored in a repository of test vectors. These test vectors are going to serve as the compliance test descriptions for Stratum-based devices. And you can either write them manually by just writing the protobuf text file, or you can generate them. And there's a language or a description language in Stratum called contract definition language, which can be used to generate some test vectors for more complicated scenarios. So once you have the test vectors, what do we do with them? These test vectors need to be interpreted by a test framework. This test framework is going to have gRPC connections to the switch under test, the Stratum-based device or Stratum-compatible compliant device that you want to interrogate using P4 runtime, GNMI, GNOI, and there may also be some additional test-only interfaces for triggering certain types of faults or failures. This switch is going to also be connected to a traffic generator using the data plane ports. And the test framework is also going to need to be able to inject things like traffic onto the test framework. These test vectors are going to be run by the test framework, and you're going to get results out like any other compliance or certification framework that you've seen. This framework can then be used for doing black box qualification. And there's 3 critical parts to the overall solution of qualifying a white box or black box, as the case may be. You start with a body of test vectors. These come from the community, from vendors, from operators. We have a set of product requirements, and then a set of open P4 specifications, Yang models like the open config models, and our interfaces that we've described. A vendor consumes these to build their product, and then when their product's ready, they can use the test framework to run tests that the community has, as well as some internal tests that they want. Once a vendor's happy with the results they're seeing, they can make a box available to an operator. The operator is going to take these, the tests, test vector tests, or some of their own tests, and they're going to first certify a box in standalone testbed, just like the Switch Vendor test framework I just showed you. When there's issues with the tests that they have, they'll work with vendors to get them resolved. When the functional tests are working, then we move on to integration tests, where we take these boxes and insert them into existing Fabric test beds, where we're going to start plugging into the SDN and management control planes that exist in our network. Problems go back to vendors, and when things are working well, actually, when those problems are also discovered, they can be used to create additional test vectors for the public repositories, or modify test vectors that may not have behaved in the ways that we had expected initially. When everything's working well, we can either move to further qualification environments, or in some cases, release. Things in release are going to be going well, production running, and eventually we're going to start to see faults or failures. Those traces that come from the SDN control plane or management plane will come back into the test environment and can be used to create new integration tests and ultimately new test vectors that can feed the body that we have. Finally, when there's new P4 specs, new models or augmentations to models, or changes to the API, that'll feed the creation of new test vectors. So this ecosystem of open source, vendor work, and operator work can together form a cycle that enables us to quickly develop and qualify these new boxes. So summarizing, there are 3 parts to Multi-Vendor SDN. The first part was open vendor neutral interfaces, which are P4 runtime, NMI, and NOI, along with open models and pipelines. So P4 programs and open config models. The second part is an implementation of these models, and that's where Stratum comes in. And the third part is an extensive conformance test framework, which is test vectors under the Stratum community. We've got a pretty significant community here. On the top, we've got a number of service providers and operators, a number of your biggest networking vendors, white box vendors, and network service providers and integrators that have all been involved. So working hard to get this Stratum working and certified on a number of boxes and platforms and available for general availability, hopefully this summer. So if you're interested in seeing Stratum in action or asking us more questions, we have a booth over in the show floor where we've got 4 different white boxes from EdgeCore, Delta, and Inventec running in a 2x2 leaf-spine fabric with about 100,000 IPv4 routes and traffic between the various leafs. So if you'd like to get involved, the interfaces, open config models, and some P4 programs are already available on GitHub. You can become a Stratum member, or if you're already on the list, reach out if you don't already have access to the project. And then if you're not interested in doing that, the public mailing list is a great place for updates and alerts when things are open and available. With that, I'd like to thank you for your time, and if we have time, maybe there's opportunity for a question. Yeah, so I'll repeat the question for those of you that couldn't hear it. So the question is, if you're going to be a blend of fixed function and programmable, you're ultimately going to be constrained by the least common denominator of your fixed function pipeline. And one thing that we can point out, perhaps, what's a good slide for this? Maybe this one, is that you don't necessarily have to use the same P4 program on every device. So generally speaking, rather than have a single pipeline for your entire network deployment, you can think about having a pipeline for a given device role. So your device roles might be a spine or an aggregation block or a top of rack. And yeah, in general, there's going to be some least common denominator that happens within a given profile or role of a device. But there's only going to be a few targets, perhaps, that you slot into that given role. And it may be that for a spine in your network, the requirements are different than a leaf. And for, a programmable ASIC is obviously going to be, more capable of filling more roles. But the roles that you have for individual pieces may still be able to not necessarily be one least common denominator pipeline across all of your devices.
Yeah, just to add, I guess the point is the least common denominator is we're not using it for the API, but rather to define a network function role. That's what it is. Thank you.
Thank you.